Hey there guys, Paul here from theengineeringmindset.com. In this video, we're going to be discussing heat pumps and comparing the different options available. Coming up, why heat pumps are efficient, choosing an air, ground or water source heat pump, and also comparing the efficiency ratings such as COP, SCOP, EER, SEER and HSPF. Just before we jump in, I want to take a moment to thank Danfoss for sponsoring this video. Danfoss has everything you need to make sure your heat pump is running at maximum efficiency regardless of what kind it is. They've put together a collection of resources on their website to help guide you to the right decisions about heat pumps. Just click the link in the video description below to access free business cases, case stories, eLessons, and even some fun diagrams similar to ones you see on this channel. Now, in the last video, we looked at the different types of heat pumps and how each type worked. In this video, we're going to be looking at how to select one and how to compare the different types of heat pumps. Why are heat pumps efficient? If we look at conventional heating methods, a gas boiler or furnace has an efficiency of say 85%, so to provide 10,000 kilowatt hours of heating over a heating season, then we need to input 11,765 kilowatt hours of energy from gas. That's because we need to combust fuel and then try to capture any heat it produces before it leaves and enters the flue. Inevitably, we cannot capture all of it, so some of it will go to waste. An electrical heater is 100% efficient, so to provide 10,000 kilowatt hours of heating, we need 10,000 kilowatt hours of electricity. For this, we're turning electricity directly into heat through resistance. We can't get more heat out than the energy we put in, so we can only get 10,000 kilowatt hours out. An air source heat pump is maybe 400% efficient in comparison, i.e. it has a COP of 4. We'll see what that means later on in this video. So to provide 10,000 kilowatt hours of heating, then we need to input 2,500 kilowatts of electricity. Sounds pretty magical, right? Well, there's no such thing as magic. What that means is we will use 1 kilowatt hour of electricity to capture 3 kilowatt hours of heat from the outside ambient air, and this will produce the 4 kilowatt hours of heating. The electricity is used by the compressor to send refrigerant around the system and capture the heat from outside, then bring it inside. It can do this because the refrigerant has an extremely low boiling point. For example, water boils at around 100 degrees Celsius or 212 degrees Fahrenheit. And as it boils, it carries heat away as steam. Refrigerants have a much lower boiling point. For example, R134A boils at minus 26.3 degrees Celsius, and R410A boils at minus 48.5 degrees Celsius. So even when the outside air is very cold, we can still capture enough energy to cause the refrigerant to boil, and as it boils, it carries this thermal energy away and into the building. Obviously, the warmer the outside air is, then the more thermal energy there is to capture. As the outside air temperature drops, it will reach a certain point where it becomes uneconomical for the cost of electricity consumption to capture the thermal energy. So which heat pump should we get? Well, first we need to decide if we want to provide hot water or hot air to the property. If air, then do we also want to provide cooling during the summer? Do we have access to a lake or river? If not, then we can't use a water source heat pump. Will the heat pump be installed into a new or existing property? If it's existing, then we probably also need to install larger radiators or underfloor heating to maximize the heat, as it is a lower temperature than conventional boilers. We also need to consider our budget, as the cost can really vary by the type. Finally, we can then decide if an air source, ground source or water source heat pump is best for us. Air source. Air source is the quickest and easiest to install, and it looks like a normal air conditioning unit. You can use these units to generate hot water or hot air. Some units also incorporate a reversing valve to operate in a cooling mode also. We've covered how reversing valves work in our previous video, do check that out, links are in the video description below. So the units are installed outside, and keep in mind that it will create some noise from the fans and the compressors. They need access to ambient air, so don't box them in, else this will cause recirculation and you'll be trying to extract energy from the air that you've just extracted energy from. This is obviously not very efficient and it's going to waste a lot of electricity. Now these units are the cheapest to install, but they're typically the least efficient because air has a low density and heating capacity compared to soil or water. Approximate cost to install an air source heat pump system, something in the range of $7,000 to $11,000, £6,000 to £8,000 or €7,000 to €9,000. This is going to dramatically vary depending on the location, complexity and size. Ground source. Ground source is the second most popular option. It's more commonly used for hot water production, but you can get units and systems that can reverse to provide cooling. It uses thermal energy embedded within the ground where it comes from the sun. This option is typically more efficient than air source because the ground has a higher density and heat capacity compared to air. This option requires extensive excavation, however, so it's best suited to new builds and can be incorporated within the construction to reduce costs. The horizontal type uses pipes buried in the ground at 1 to 2 meters or 3 to 6 feet. You'll typically be able to extract around 10 to 30 watts per meter of pipe depending on the ground type. Install costs are typically somewhere around $13,000 to $24,000, 10 to 18,000 pounds or 12 to 20,000 euros, but this will dramatically vary on location, complexity and size. If you don't have access to a lot of land, then we also have the vertical type, which uses a loop of pipe placed deep in vertical holes. The holes are typically somewhere between 15 and 150 meters deep or 50 and 492 feet, and you can typically extract 10 to 50 watts per meter, depending on the ground type and the water content. Installation costs are typically $18,000 to $32,000, 14 to 24,000 pounds or 16 to 27,000 euros. Again, this dramatically varies depending on location, complexity and size. Water source. The third option we have is the water source heat pump. This is the least most common type simply because the property needs to have access to a lake or river. Unfortunately, that little garden pond just isn't going to be big enough. For this type, there are two options, either open or closed loop. Closed loop uses a water plus antifreeze mixture to cycle around and capture the heat. Alternatively, we have an open type which pulls in water from the source, extracts the energy and then releases this water back into the source some distance away. This type usually has much stricter permissions required from the local authority. Consider that if the system leaks and the refrigerant or the antifreeze mixture gets into the water source, it's going to be toxic for the wildlife and you might even receive a fine from the Environmental Protection Agency. It's pretty rare for it to leak though, but it has happened. However, this option is very efficient, more so than air or ground source. The pipes are constantly surrounded by water and the current and flow of water means that the energy source is constantly replenished. It's also fairly easy to install and much cheaper to install than ground source. Typically, a water source unit can provide around 20 to 60 watts per square meter of water surface. Cost to install typically around 10 to 15,000 US dollars, 8 to 12,000 pounds and 9 to 14,000 euros, again dramatically varying with location, complexity and size. Comparing different units and their efficiencies. There are many standards used across the world for assessing the efficiency of heat pumps. I'm going to just cover a few of the most common ones, focusing on units made in the US and the EU. COP. COP values, or the coefficient of performance, is used worldwide for both heating and cooling. It's simply the heating or cooling output divided by the electricity input. It's not a good indicator of efficiency, however, because it only gives a snapshot of how a unit should perform under very precise conditions. For example, this unit has a heating COP of 2.9. But when you read the small print, that was achieved when the outside air was -3 degrees Celsius dry bulb and -4 degrees Celsius wet bulb, while providing 35 degrees Celsius water for 8.3 kilowatts of heating and consuming 2.86 kilowatts of electricity. As the outside air temperature varies hourly and daily, this is not a good indicator of efficiency. We reviewed the manufacturer literature of many air source units and found them to vary between 2.75 and 6.13. SCOP, or Seasonal Coefficient of Performance. You'll see this on European units to measure their average heating efficiency. It's a much better indicator than just the COP. The manufacturer has to test the performance of their units at different outside air temperatures. The unit is expected to operate at a specified number of hours at each temperature per year depending on where in Europe it's located. There are 3 zones: warm, average and cold. The heat supplied and electricity consumed for the specified operating hours at each temperature is accumulated and divided to give an average COP for the year. The SCOP also considers the energy consumption for things such as standby mode and crankcase heating. You'll see stickers like this on EU-produced heat pumps, which lets the buyer quickly and easily see how the unit is predicted to perform depending on which climate they're in. We reviewed a number of air source units for our domestic purposes and found that the typical SCOP values lay between 3.9 and 5.2, with a higher number meaning more efficient. EER, or Energy Efficiency Ratio. This is a measurement of a unit's cooling efficiency that's mostly used in the US. It's a ratio of a unit's cooling capacity in BTUs divided by the watts consumed to produce it. This is only tested at one condition, generally 95 degrees Fahrenheit outside air temperature, and has a return inside air temperature of 80 degrees Fahrenheit at 50% relative humidity. So it's not recommended to use this to estimate your annual energy consumption or assess how the unit will perform in your location unless you live in a hot climate. However, it is a good way to compare units by different manufacturers for peak summer load. From the units we reviewed, we found units rated between 11 and 16, with the higher the number, the more efficient it is. The SEER, or Seasonal Energy Efficiency Ratio, is used in both the US and the EU on units which operate in cooling mode. Manufacturers will calculate their unit's SEER value by testing it at a number of different outdoor temperatures to represent a cooling season. The units of measurement are different, with EU models calculated on watts of cooling per watts of electricity, and US models calculated on BTUs of cooling per watts of electricity used. In both cases, this is suitable for units installed in very average climates. If the unit is installed in a hotter or cooler part of the US or EU, then it will not accurately represent how the unit will perform. So it's a good way to compare different units, but not a good way to calculate the energy consumption unless you live in an area with pretty average weather conditions. Typically, you can find SER values for US units between 14 and 24 and EU units between 5.25 and 7.2. The higher the number, the more efficient the unit is rated. HSPF, or Heating Seasonal Performance Factor. This is used in the US for the heating mode of air source heat pumps. It is the ratio between heat output in BTUs over a heating season divided by how many watt hours of electricity were used to produce it. It also takes into account supplementary electric heating. Manufacturers calculate their unit's HSPF from testing it at defined different temperatures to represent a heating season. This is an estimate of how the unit will perform, and it may not actually perform like this in reality, especially if the unit is oversized. It is a good way though to compare different units. Typically, a unit will be between 7.7 and 14, with the higher the number, the more efficient the unit is rated. I just want to thank Danfoss again for sponsoring this video. Don't forget to check out their heat pump solutions by clicking on the link in the video description below. Okay guys, that's it for this video, but if you want to continue your learning, then check out these videos and I'll catch you there for the next lesson. Leave your questions in the comment section below, and don't forget to follow us on Facebook, Instagram, Twitter, as well as theengineeringmindset.com. Once again, thanks for watching.